We're now going to take a look at the general addition rule, and the general addition rule is important because in our last video when we were just doing addition, we were always dealing with situations where there was no intersection between the two events. In this case, we're going to deal with events where there is in fact some intersection, and so I can't just add the probability that A occurred and the probability that B occurred, because then essentially I'm adding this twice. So let's take a look at that rule that helps when they're disjoint or not disjoint. So again, we're leading up to the fact that not everything is disjoint and independent. And so when we're talking about the general addition rule and later the general multiplication rule, it's going to take into account that not everything is disjoint and independent and give us a strategy for dealing with that. So again, to help us to see the probability of all of the outcomes in our sample space, we're going to use a Venn diagram, and we've chatted a little bit about this before. But we know, and I've tried to put these throughout the videos, when I highlight, it's so when you're dealing with just a question that I throw at you and you're thinking, gosh, do I use the general addition rule? Am I going to multiply? Am I going to use a tree diagram, which we're going to talk about later? Hopefully you can look back at this and say, okay, I know to use a Venn because I'm dealing with one population and I have events that are not disjoint, which means I have events where I could fall into both categories, like I own a smartphone and I own a computer. So let's take a look at a question here. We have 100 people are attending a play. And of course I used 100 because this is going to make it really easy for me to turn anything into a percentage. And it says 84 are from Omaha. So again, I'm just going to write that as 84% are from Omaha. 48 are men. So that's 0.48. And 40, or 0.4, are men from Omaha. So I've already done this. I've already switched everything to probabilities. And then I want to fill in the diagram to answer the questions. So here's the mistake a lot of people make. They say, okay, 84% are from Omaha, so that's 0.84. And then 48% are men, so that's 0.48. And then 0.4 are men from Omaha. Now, remember what I said is everything inside of this, including the stuff outside of the circles, has to add to 1. And if I took 0.84 plus 0.4 plus 0.48, that is greater than 1. It doesn't matter even what the sum is, I just know that it's greater than 1, and that's not okay. Which means I can't use these values just as they are. Now the good news is I can use this value. And essentially that's where I typically start, is to start in the middle and say, okay, 40% are men from Omaha. Now, typically, you are not going to see this label in here. I wrote that label just so we could understand that that's what we're dealing with. We know that because this is the area that is in both Omaha and men, that the intersection must be men from Omaha. So I got 0.4 for men from Omaha. Now, how do I then determine how many people are from Omaha that are not men? And so here I can take the 0.84 that I had originally written and subtract the 0.4 that's here in the middle, because if I subtract that, I'm going to find out how many are not in that intersection, and that gives me 0.44. So 0.44 are from Omaha, but not men, which of course means women from Omaha. Men is 0.48 total. 40% are men from Omaha, which means if I take 0.48 minus 0.4, and if you need to add that 0.40 because we're subtracting place values here, and I end up with 0.08. So 8% are men who are not from Omaha. Now, what's left? I've got these people out here who are not men and are not from Omaha, which of course means women that are not from Omaha. And how do I know what that is? Well, I have to take my 0.44 plus my 0.4 that's in the intersection plus my 0.08. I'm adding up the 3 that I have circled, and I find that to be 0.92. Now, I already told you that everything inside the box has to add up to 1 because that's the total sample space. And so I'm going to take 1 minus 0.92, and that is going to be anything not Omaha, not men, which is women from not Omaha. So now that I've done all of this work, that's all the hard stuff. This is the easy stuff, the answering the questions once I make my Venn. So the probability someone is either from Omaha or a man. Well, everybody in this circle is from Omaha, and everybody from this circle is a man. And so I can just take 0.44 plus 0.4 plus 0.08, which, hey, guess what? I already did that, and get 0.92. So again, notice I didn't add the 0.84 and the 0.48. I added the values on my Venn. Second, what is the probability that the attendee is a woman? So that would be people who are, let me find a different color, people who are from Omaha but didn't fall in that men from Omaha category, and people who are not men, which means women, and not from Omaha. So I would take 0.44 plus 0.08, and I would get 0.52. So that's one example where we could use a Venn diagram. So you might be asking yourself, well, what does making a Venn have to do with the general addition rule? And the answer is that we could in fact be able to answer those questions that we did before using the general addition rule, which is this, without making a Venn. So remember previously when I said the probability that A or B happened, I just added the probability of A and B. So if I said the probability of, rolling a 2, which is 1/6, plus the probability of rolling a 4, which is 1/6, I would add those together, and then I would find that as a decimal. But now I have a situation where my events are not disjoint, which means it could be that it falls into more than one category, which makes it more confusing. And what that does is takes the probability of A plus the probability of B, but it subtracts the intersection. And let me give you a visual so that you understand why that is. So I'm going to look at the same example that I had before, where I had Omaha and I had men. And remember, initially we said 84% of people were from Omaha. And so if I would have put 0.84 here, and we know that's wrong, I should have put 0.44. But if I put 0.84 there, and then I look at man, which is 0.48, essentially what's happened is this value in the middle, which is the 0.4, was added twice. It was added once to the people from Omaha and once to the men. And so because it was counted twice, we have to subtract it once. So notice here I'm taking, instead of having to do the subtraction and turn 0.84 into 0.44 and turn 0.48 into 0.08, I can say let's take all of the people from Omaha plus all of the people who are men, and then subtract the people who were counted twice, which is people who fall into both categories, men from Omaha, which is the 40%. And notice I get the 0.92, which was the same answer that I got before when I added the 0.44 plus 0.4 plus 0.08. That was the same answer that I got the other way. So right about now you might be thinking, hey, that little formula is great, but I'm not going to do it. I'm just going to draw a picture every time, and I'm sure it'll work out just fine. Well, let me give you an example where, unfortunately, we're going to have to use a little bit of math. a little bit of an advanced math, or this formula, the general addition rule, to figure it out. So here we say a survey of college freshmen revealed that 57% of college freshmen were registered for math, and 70% were registered for math, English, or both, and 34% were registered for both. So all I can do right now is I can put that 0.34 on here, and I can figure out the number that should go over here, because if math is 57%, I should be able to take away 34% and figure out how many are just in math but not English, and that of course would be 0.23. But what I'm looking for is, I don't know English, and I don't know that part on the outside, and how am I going to figure that out? So I can use this formula that says we have the probability of A union B. That's everything, right? That's this value right here. So essentially we're saying 0.7 is equal to the 0.57, which is math before I took everything away, plus the probability of English, which is what I'm trying to figure out, minus the probability that it's in both, which they've already told us is 0.34. So again, that's how I'm going to figure out the probability of English, and that would be everything in the English, including the 0.34. But let's go ahead and move forward with this. We can say 0.7 is equal to, if I took 0.57 minus 0.34, guess what that gives me? 0.23, because I already did it, and I figured out that's who is in math, and I'm saying probability of English plus 0.23 should be 0.7. So now if I subtract 0.23 from each side, I'm going to get 0.47, and that's going to be the probability of English. Now remember, that's 0.47 in the entire circle of English. So now I still have to take 0.47 minus 0.34, and I would end up with 0.13. That's just in English. Now, how do I find out that number on the outside? Well, that one's actually super simple, because if I know 70% are in math or English or both, which means 70% are within the circles, then 30% are not in the circles. So now I should be able to answer the questions, which are the probability that a freshman wasn't registered for either class. That's 0.3, this guy on the outside. What's the probability that a freshman was registered for English? Well, English is everything inside the circle, so that's my answer down here, 0.47. So again, did I have to make a Venn diagram to answer this? No, I didn't, but I had to know some information about the general addition rule. So here's an example for you to try on your own. So create the Venn diagram and then find the probabilities that I've asked for. Once you've done so, then press play to check your work. So again, the first thing I would do is to go ahead and make a Venn. And I'm dealing with data display, and I'm dealing with an equation. So I'm just going to abbreviate with D and E. And it says 48% have some kind of data display, 27 have an equation, 7 have both. So 0.07, I made that very small, I apologize. 0.07 is that little nugget in the middle. And to find out what goes in D, I have to take 0.48 minus the 0.07, which is 0.41. And to find out what goes in E, I have to take 0.27 minus 0.07, which is 0.2. To find out what goes on the outside, I essentially have to take 0.41 plus 0.07 plus 0.2, and then subtract that from 1. So this gives me 0.68, and 1 minus 0.68 gives me 0.32. So that's the number that goes out here. Once I've made my Venn, now I can answer these questions easily. A randomly selected page had neither data nor an equation. That would be that 0.32 on the outside. A randomly selected page had data but no equation. That would be my 0.41. So data but no equation means it wouldn't fall in that intersection. One more for you to try on your own just for good practice. A survey of families revealed 58% of families eat turkey at holiday meals, 44% eat ham, and 16 have both. Make a Venn diagram and then answer the questions. So, go ahead and press pause, try these questions. You should be a pro at this point, and then press play to see how you did. So again, the first thing I would do is find the probability, or find my Venn diagram. So I'm just going to make it kind of small up here in the corner out of the way. I'll try to make that intersection a little bit bigger. And again, I usually start, if I can, with the value in the middle. So 0.16 goes in the middle because that's turkey and ham. We'll call this turkey, we'll call this ham. So if 58% eat turkey, I'm going to take 0.58 minus 0.16 to find this 0.42. And so remember, just so we're clear, this 0.42 is people who eat turkey but don't eat ham, because the people who eat both are in the middle. And then I would take 44%, which eat ham, and I would again subtract the 0.16 to get 0.28, and again, so we're clear, that means 28% of people eat ham but not turkey, because the people who eat both, again, are in the middle. To find the people on the outside, I would add 0.42 plus 0.16 plus 0.28, subtract it from 1, and I get 0.14. So now I've got my Venn, I can answer my questions. What is the probability that a family had neither turkey nor ham for their meal? So again, that would be my 0.14, which is these guys on the outside. No turkey, no ham. What is the probability that a family had only ham at their holiday meal? That's these guys. Only ham, no turkey would be 0.28. Last question, are having ham and having turkey disjoint? So two ways to look at this. You can reason through it, or you can look at your picture. Now if I look at my picture, I can see there are people in the intersection, and therefore, no, they are not disjoint, they overlap. That's what disjoint means. Do they overlap? Okay. The other way is to just reason through it. Is it possible that a person had ham and had turkey? So again, looking at my information, we know, yes, 16 had both turkey and ham, and therefore they are not disjoint. Oh, look, I had a nice Venn diagram all done for me already. So they are not disjoint because some families had both ham and turkey.